yeah, you and I will be able to get the state vector, right, at every instant of time, right? So that is the overall idea of what is called as observability. Okay, so this is the definition of observability. So the motivation or the physical motivation behind the concept of observability is whether you and I can estimate the state with limited measurements. So mathematically, it's posed as a problem where we want to figure out whether given an input and the measurements y, can we get the initial state vector x naught, right? If we are able to do that, then we are essentially able to get this x at every instant of time, right? So that is why the definition of observability is written in the way. From an engineering perspective, this is important. Okay, so yeah, all this mathematics is fine, but then like as an engineer and even as an automotive engineer, what do I interpret? Okay, so the notion of controllability, as we gain more experience in this field, we will realize that controllability has to do with actuators, whereas the notion of observability has to do with sensors, right? So when we are designing practical systems, right? So we can smartly choose sensors such that we make the system observable, right? Or we essentially ensure that we are able to estimate the states, right? As per our requirement. So similar to checking for controllability, we can have a criteria for checking for observability. So we construct what is called as an observability matrix O. So these are the observability matrix for MIMO systems and CISO systems. For MIMO system, it's the output matrix C, CA, CA squared, all the way till CA n power minus 1, stacked in a column. For CISO systems, it is the column vector C, A transpose C, A squared transpose C, all the way till A power n minus 1 transpose C. That is an n by n matrix, and we take the transpose of it. Okay, so that's what is called as the observability matrix. Okay, so the condition for complete observability is that like the system is observable if and only if the rank of the observability matrix is n. Okay, so for controllability, we realize that the rank of the controllability matrix should be n. Similarly, for observability, the rank of the observability matrix should be n. Okay, so that is the criteria. So this is quite important. Okay, so that is like we want to ensure that we have systems, right? Or we have measurements, right? From which you and I can get the state estimates. Okay, so and then like we can then design state estimators. Although that's not within the scope of this particular course, when we deal more in the state space control methods and estimators for practice and so on, even in automotive applications. Okay, so in many automotive applications, the Kalman filter is used as a stochastic observer, right, or a stochastic state estimator, right? The idea is this: that is, like, can we, get the estimates of the states, which we then utilize in, let's say, if we have full state feedback, we design that. So we know that the control gain is designed by us. We did a few examples. So when we want to implement the controller in real life, we use the estimates, right? Estimates of states that are not measured. Okay, so those are used to do the calculation of the controller. Okay, so that's what happens in practice. So if you look at a couple of examples, let's go on. So we would have seen that in some problems I would have written this script O, right, which is the observability matrix. Now we will know what that is, right? So even if we take this example, which we already did for full state feedback controller, if you and I were to check for observability, we form the observability matrix O, which in this case is C and A transpose C transpose. Okay, because why? The value of n is just 2. Okay, so we only go to A power n minus 1. So we put C. C is 1 and 1. Okay, that is the output vector here. And A transpose C, you and I can calculate, right? The transpose of A is this matrix transpose. Okay, so it becomes 2, 3, 0, 1. And then C is this vector. So the answer becomes 2 and 4. So the second column of the observability matrix is 2 and 4. So if you transpose it, we get this. And we observe that the rank of this matrix is 2. Okay, so the system is completely observable. And when we have a system to be completely observed, right? When we have the realization A, B, C, D of a system, right? To be both completely controllable and completely observable. That particular realization is what is called as a minimal realization. Okay, so this is all like a terminology that you and I should be aware of. Okay, so now if we look at another example, right? We did one more example where we had this as the system. Once again, if we calculate the observability matrix, it's C and A transpose C transpose. So C here is 1, 0. A transpose C is this 0, 1. So we essentially get this as the matrix. Immediately we can observe that the rank of this observability matrix is 2, right? So consequently, this is also completely observable, and we already saw that it's completely controllable. So obviously, the system is minimal, right? Or the realization is minimal. Okay, so that's something which we can readily conclude from these examples. Okay, so I hope the broad picture of what we want to do with observability is clear, right? So while controllability had to do with controlling the system, right, by choosing the appropriate input or calculating the appropriate input U, which is a function of X, the notion of observability was towards estimating this X, right? Such that you and I can calculate this. Okay, so the overall point is that like we want to get the estimate of the state vector X, which will ensure that we are able to calculate the control input U from the estimates and still, like implement the control. Okay, so that's a very practical tool that we have. Okay, so this is the notion of observability, right? So the last concept I want to share in this course is more for information. Okay, so that is like, I just want to share that such tools are available. In fact, when some people look at suspension control and all, they talk about this linear quadratic regulator and so on, right? That goes into the realm of what is called optimal control. That is, we ask ourselves the question, we know that, the control input U is K times X, right? Where K is the control gain, right? The question that we ask is that like, can you and I calculate this gain K in an optimal manner? Okay, so can we optimally choose the control gain K? Okay, so one very popular, controller is what is called as a linear quadratic regulator. It's a very interesting term, right? Because the word linear and quadratic are sort of like contradictory to each other, right? A linear function is certainly not quadratic, and a quadratic function is not certainly linear, right? Then what do we mean by telling that, oh, okay, a regulator or a controller is linear and quadratic? Okay, so the way we should interpret this is that this controller, LQR, which is a very common abbreviation, is for a linear system. Okay. However, it is designed, the controller is such that a quadratic performance index, which is given by this big formula, is minimized. Okay, so we will not get into the mathematics here, but I hope the idea behind LQR is clear, right? So the regulator or the controller is still applicable for a linear system, but then like it is applicable for a linear system with a quadratic performance index. Okay, and we want to minimize the quadratic performance index to get the corresponding control input. Okay, so that is what you and I are interested in. Okay, so and it finally turns out that if we solve this problem, you and I can get analytical solutions for this control gain K by solving what is called as a Riccati equation. Okay, So as I told, this final part is only for your information. We will, I will not ask you any questions about linear quadratic regulator in the exam. Okay, it's just for us to know that there's something like that. So predominantly our final exam syllabus ends here. Okay, with observability. All right. So for a final exam, I think we will start from frequency response and then like we will go till observability. Okay. So that is going to be the syllabus for the final exam on May 9th. Okay. So this brings us to the conclusion of our theory discussions for this course. So broadly, like we learned the control methods in both the transfer function representation and the state space representation. First look at the transfer function representation. We design the closed loop feedback system. We learned terminology associated with it. And finally, we learned methods like root locus, Bode plot, and so on, right, which were useful for control design and analysis. Then we came to the state space representation. We looked at solving the state equation. Then we looked at what is called equilibrium state, stability of an equilibrium state. Then we looked at the notions of controllability, full state feedback controller, and finally observability. Okay, so these are the main concepts that we learned in this particular course. And as I mentioned at the beginning of the course,
I'm sorry, sir. Can I sir, ask one question, sir, if you allow me, please?
Yeah, please go ahead.
So basically, while you are teaching us the concept of how to solve the state space equation, right, sir? So basically, you had told us that there is a typical condition that arises where we can take the differentiation of matrix like e to the power like matrix A into T, something like that.
Yeah.
And then when you want to find it, and if it is diagonal matrix, then we can just multiply with the coefficient in that sense. Replace that. Are you getting a point, sir? I'm sorry.
Yeah. What is the question, Roshan?
So, sir, my question is that the question, the portion of the exam will limit it to 2x2 matrix only, right, sir? What I mean to say, if it goes beyond 2x2 matrix, then probably we have to focus more on algebraic concepts and all those things.
Okay. So you want a clarity on what will be the scope of the final exam, right? As far as the order of the system is concerned.
Exactly, sir. I'm sorry to disturb you in between, but I just
no problem. I think that's a very important question. It's a practical question also. I think maybe first we will listen to a leader Arunachalam. What does Arunachalam say?
Okay, sir. Arun sir, are you there?
Hello, sir. Sir, can you hear me, sir?
Yes, Arunachalam. The question from Roshan was that in the final exam, can you restrict the questions only to second order systems? Am I correct, Roshan? That's what you right? Yeah.
Yes, sir. That is what we understand, sir.
That is what all of you want, right? Okay.
Yes.
All right. Okay. So I will give you that assurance. Okay. So in the final exam, you have only up to second order system. Obviously, first order systems is not fun. Okay. So I think I need to relook and then change things if necessary in the paper. No problem.
First order is already you have taken a no issue, sir.
I'm sorry. What is it?
Sir, if the question in paper already you set by with the first order, then it is okay.
No. What I told was that first order, certainly I don't think I would have set questions, but I will go back and check whether I set something with third order or more. Okay, if yes, I will change everything to second order. I hope that's fair enough, right? Yeah.
Sir, we all should pass, sir. That you should assure, assure, sir.
No, anyway, I'm sure all of you will easily pass. I think the question, the expectation should be on excelling, right? Not on passing, right? So,
of course, sir.
No, sir. Roshan is saying pass now means he wants only yes, sir.
Okay. Yeah, I think everyone's expectation will be different. Okay, I agree. Yeah. So, but more important than the grade, it's about learning.
Yes.
So as I was saying, the way in which I chose the topics in this particular course is based on my own research group's research. Right, I collated topics which I felt were important. For this particular field. Okay, and that is what I have taught in this particular course, right? So of course, but as we know, there always needs to be a balance between theory and practice, right? So see, even when we talk about PID and so on, right? Unless otherwise you and I learn the theory, it's very difficult to practice, right? So we had to go through the theory. Okay, so there was no other alternative. But I do hope that at least this basic discussion will stimulate more interest, okay, as you go forward in your career. That is the expectation. Okay? So now, any questions before we close down the lecture sessions?
Sir, am I audible?
Yes, please. Sir.
Prem here. So, just a couple of questions. One is on this observability for continuous time system versus a discrete time system. It'll be different, or the approach will be same?
Yeah, see, ultimately there will be a criteria, once again, an observability matrix with the corresponding realizations. But the notion is the same, Prem. So see, continuous time and discrete time is only a matter of convenience. Okay, depends on how you and I are looking at time. Okay, but the physical notion of observability and controllability remain the same. That is, see, a system is a continuous process, right? The question is, you and I sample in a discrete manner, we want to analyze in the discrete domain. That is our choice, right? Yeah. Okay. So, but then if you look at this particular thing, we essentially want to, have, the physical definition of controllability and observability, right? They remain the same, okay, irrespective of whether we have represented a system in the continuous form or the discrete form, okay. So what do I mean by that? Controllability is controllability, okay. Doesn't matter whether we write the system's equations in the discrete form or the continuous form. And same thing holds for observability. Yes, the tools and the analysis process may slightly change, okay, depending on the some the unique characteristics of both the representations, right? Whether we are writing in the continuous form or the discrete form. Okay?
Noted, sir. Got it. One question on the mathematics part of it. This term called full rank. What is the meaning of a full rank matrix?
Full rank means, see, if you have any matrix A, let's say for the sake of simplicity, we start with a square matrix. Okay, full rank means
equal to n.
Rank should be n.
Okay.
Okay. So what is rank of a matrix? A rank of a matrix is the maximum number of linearly independent
coefficient.
Linearly independent columns or rows. Okay.
Right.
Yeah. Okay.
So that is what is meant by the rank of a matrix. Okay. However, when we have a non-square matrix, okay, full rank means, see, rank of a non-square matrix is can be at most the minimum of the two quantities, m and n. Okay, if a matrix A has m rows and n columns, if the rank of the matrix can be at most a minimum of m and n. Okay, so the point is that we essentially call a non-square matrix as a full rank matrix if the rank of the matrix is going to be the minimum of the number of rows and the number of columns. Okay, that is what is called as a full rank matrix. Okay?
Got it, sir. Thank you.
Right? Any other questions? No.
Sir,
Hi,
am I
please.
audible, sir?
Yes, please. Please go ahead.
Sir, the condition for checking the like observability that you have taught now, just now, MIMO and CISO.
I'm sorry, what is that?
That MIMO and CISO system, sir,
Ah.
where the matrix A is N cross N and matrix C is basically P cross N, right?
No, 1 minute. Yeah, which slide are you talking about? You know,
Condition for checking observability, sir.
which one? No.
Just go up, sir, a bit. I'm sorry.
Okay. Here.
Yeah,
Is
here.
it? Yeah, okay.
Yes, sir. So, sir, you have taught us that for the MIMO system, like unlike CISO, the C becomes a matrix, right? If I'm not wrong.
Memo system. Yes, C is a matrix. Correct.
Matrix. But for CISO, it is C is not a matrix; it's a vector. If
C
I'm
is
not
a
wrong,
vector.
right?
Correct. Mhm.
So, sir, see how this interpretation, like here C is what I mean to say is this and all those things, and here it is transposed up from that. So
yeah.
just wait on
Yeah.
this topic,
So
sir, please.
So essentially, if it gives comfort, Roshan, in the final exam, I will ask only CISO. Okay, point number 1, right? Yeah. So that I think the entire class can be focusing on the physics rather than the mathematics. Point number 1, right? Now, if you look at the CISO system, what is the C? C is a column vector, right? Is it not 1, 0?
Oh, right, sir.
Right? And the matrix A is 0, 1, 2, 1, minus 1. Okay. Now, if you look at the observability matrix, what happens is that it becomes C and A transpose C transpose. Right. So what happens to C? It is 1 and 0. Now, what is A transpose C? It is 0, 1, 2, minus 1, multiplying 1 and 0. So if you do this matrix vector multiplication, we will end up with 0 and 2. Sorry, 0 and what will I get? It should be A transpose, right? Sorry. I'm sorry. There is a mistake here. A transpose means this will become 0 and
0,
2.
2, 0,
1.
2, 1 minus 1.
So this will become 0 and 1. Okay. So A transpose C also becomes a column vector, which is 0, 1. And when you transpose this resultant vector, you get the same because it's a diagonal matrix. So this is a full rank matrix. Okay. So that's how we get this, right? I hope it's clear, right?
Right, sir. Right, sir.
Okay, any other questions?
Sir, can we ask some question from the back slides also? If
Yeah.
possible?
Please go ahead.
Sir, if you can go a bit where you have written a question like what happens to the plant transfer function under a similar. Yeah. Go up, sir. Go up a bit.
Under a similarity transformation.
Exactly, sir.
Similarity transformation, the plant transfer function remains the same, Roshan. Okay. So that means the plant transfer function is unique. All right. So only the state space representation changes. Okay. So even if you calculate the new plant transfer function, I think this is one, right? Yeah. So
right,
you will see that you will calculate. Of course, see why did I not do all these derivations here? It is because we have the mathematics should not sort of hide the physics. Okay, so the mathematics will become a little bit more involved. Okay, but that is not the agenda of the course also. But you can take it as granted. Okay, so these are only exercises for you to solve. Okay, yeah. If you are more mathematically inclined. So you can be assured that under a similarity transformation, while the state space representation changes, the transfer function representation remains the same. Okay. Yeah.
So that was just to show that the transfer, state space, representation is not unique in that sense, right, Nazar?
Yeah,
That was intent.
correct. That we discussed, right? State space representation, there can be infinite state space representation, but transfer function, there is only one. Okay.
Right, sir. Thank you.
Right. Any other questions? So Arnachalam, is everyone present today? No.
Yes, sir, everyone is present, sir. Sir, we note down we will work out all the assignment problems, sir. So, and anyway, we are going to prepare for class number 14 to 32. In the meantime, I will collect all the doubts and we can have one class.
No problem, Arnachalam. You can send me a email, whenever there needs to be a doubt clearing session. We can schedule it at a mutually convenient time, and then all of us can discuss. Absolutely no, right?
And just one question. This observability, only if it exists, we are going to go for getting the feedback from output, right? Only then we'll be going for getting
So I think observability, if it exists, it
Yeah.
will facilitate estimating the state variables from available measurements. Okay. Now,
Okay.
the opposite question is that, right? Suppose if the observability, right? Yeah, is not satisfied, then what do we do? Correct. So then we have what is called as detectability. Okay, so we can go ahead even if the non-observable states are stable. Okay, so there are finer points, Prem, which we have not discussed in this course. But when you take a advanced level course on control theory alone, there we will discuss all this. Okay, yeah.
Got it, sir. Got it.
And sir, one last question I want to ask. I'm sorry. Sir, while teaching the Bode plot, okay, you had taught us that suppose we are having suppose s plus 10 divided by s into s plus 1 into s plus 10, something like that. Then we have to just divide in the bricks for individual, what I mean to say, in the form of constant k, s, 1 upon s, or something like that. And then plot individual and then find the resultant.
Correct.
But at the same time, you also taught us that for the second order system, there is a uniqueness of what I mean to say is Bode plot, where the slope changes by minus 40 dB, right, sir? And then we have a compensation for what I mean to say is zeta and all.
Right.
So why can't we suppose, sir, if we have given just to draw what is the Bode plot of s divided by s plus 1 into s plus 2 for time being. So can't we just what I mean to say is solve 1 divided by s1 s plus 1 plus s plus 2. So we can do it multiply the s plus 1 and s plus 2 and form a quadratic equation, and then accordingly whatever quadratic equation that you have concept you have taught us, that we can apply out or not.
Okay, I got your question. Let me clarify. Okay. So let's say I am taking your example, right? S plus 1 times s plus 2 in the denominator, right? You multiply s squared plus 3s plus 2. You will see that, please note, Roshan, the subtle point there is that we consider the standard second order factor in Bode plot when you and I are not able to factorize the second order factor as two first order factors with real roots, right? That is, zeta was only between 0 and 1. Okay, what we learned as corresponding to an underdamped system, right? When you and I are able to factorize the second order factor as two first order factors, we use the steps for Ts plus 1 and 1 by Ts plus 1. I hope that clarifies your question, right? If you want to dig deeper, you will see that this is like an overdamped system, right? The denominator polynomial of an overdamped system, because you have zeta to be greater than 1, right? If you calculate zeta.
Amazing, sir. I could easily get all dots is clear now. Thank you so much.
Sure. Right? Any other questions?
Yes, sir. As of now, it's clear.
Okay. So then, if there are no further questions, thanks for attending all the lectures. So I will
Thank you
wait
so much,
for
bro.
I'll wait for Arunachalam's message for a doubt clearing session whenever needed, and Abhinav will continue interacting with you from tomorrow, so that you can all complete the projects. And I believe you submitted till homework 3. Am I correct? Next.
Correct, sir.
Correct, sir.
So homework 4 and 5, please submit on May 9th. Okay, when you come here, right? And then we will have the final exam, and I will grade and submit the marks as soon as possible. Okay, yeah. So I think thanks for attending the lectures. I think it's been always a joy interacting with your batch. And anyway, I'll meet you during the doubt clearing session and also during the final exam. Okay, all the best.
Thank you,
Thank you, sir.
Thank you very much, sir.
It's a pleasure learning from you,
Thank you,
sir.
sir.
It's really nice experience.
Thank you. Bye bye.
Thanks a lot, sir.
Thank you. All the best. Bye.
Bye, sir. Thank you, sir.
Hello?